Welcome back. If you don't know me, see the previous portion of this talk. As a reminder, this talk is part 2 of a 2-part talk here at CppCon. The previous time I talked about micro design, overload sets, parameter passing, method qualification, etc. And this time we're going to talk about types at a higher level, type design, and all of the getting up into type design theory. But first, a prelude. Once upon a time, Euclid wrote out the rules for geometry. You can draw a line between 2 points. You can extend an infinite line from a finite line segment. You can draw a circle with any point in radius. All right angles are equal. And it takes, these are 4 rules, but it takes 5 rules, 5 postulates to underpin everything that there is about geometry in 2 dimensions. 4 of them seem like, well, yeah, okay, that's pretty fundamental. And the 5th is sort of weird. 2 lines that are parallel to the same line are also parallel to each other. Geometers tried for almost 2,000 years to prove this last one in any variation, based only on the good ones, because this does not feel as fundamental. There is a difference in this rule. In the end, however, what we discovered is that variations on that rule, in fact, describe other self-consistent forms of geometry on a non-planar 2D surface. This 5th rule, the parallel postulate, is indeed weird, is indeed different than the other basic rules. But it's different in ways that can be examined and mined to come up with useful results. Enough foreshadowing. When we left the previous talk, we were looking at how const methods were both a micro-property, a property just of a single class method, as well as a macro property in the space of thread safety. That is, in addition to being a statement, this method can be called on a const object, const methods are those that can be called concurrently in a thread-compatible type without synchronization. That is why, for example, it's okay to call .size on the same vector from 2 different threads at once. And that we know that based only on looking at the type signature. The method is const, so it's not mutating the object, so we have no API races nor data races. If any other non-const operation is being invoked concurrently, that is a whole different story. For a much better treatment of all of that, and for explanation of all of the terms of art I just used, go see Jeff Romer's talk on Thursday. Most of what I know about thread safety and how it interacts with type design I learned from him. But anyway, in this talk, we are looking to produce a taxonomy of properties for type design. Or put another way, in what ways can the design of a type vary? When you're describing a type, what terms do you use as shorthand to describe its design and usage? Which combinations of those properties work well together, and which are just bad? So of course there's thread safety. We already basically foreshadowed that, right? You can have thread safe types, that's good. You can have thread compatible types. That should probably be your default. Thread safe types, you're probably paying for in some fashion, either through synchronization costs or through API constraints. Thread compatible types, your default, can be, const methods can be invoked concurrently. Non-const methods need synchronization. And this fits very nicely with the sometimes aspirational philosophy of C++ that you don't pay for what you don't use. If your program is single-threaded, you aren't paying for synchronization on a vector for all of the operations you do on the vector. Vector is thread compatible. Then there are thread unsafe types. These are almost always just mistakes. It is very rare to write a thread unsafe type intentionally these days. I've seen 3 or 4 in the last couple of years. Every single one of them was a bug. There are some interesting theoretical scenarios where they could be fine. You could use thread unsafe types in thread local storage, or you could leave members mutable in an unsynchronized thread compatible type when there's no parallelism. For example, you could take a bunch of the overhead out of shared pointer if you know that that pointer is only ever going to be used on one thread. In practice, I've never seen anyone actually optimize for this use case and not regret it. I would be deeply skeptical. Thread unsafe types are hard to use. They require a lot more knowledge of the behavior of your program. This is single-threaded, this type is only accessed via X, etc. That idea is worth reiterating. These types, thread-unsafe types, are harder to use because they require more knowledge of the structure of your program. Real briefly before we go on, there are going to be a handful of slides like this as we build up our catalog of type properties. And generally speaking, I'm trying to list all of the common options for how a type might be classified for this given property, and then judge that choice. Trying to compress down the full context of your problem is pretty lossy, but these slides will capture a lot of the basic practice for type design. Like in this case, by default, make it thread compatible. If you've got reason, make it thread safe. Almost never make it thread unsafe. For thread unsafe and other bad options, I will try to discuss full type designs later in the talk across all the property dimensions that might make it usable. This is not always a complete list. So let's look, what are the other properties that we might talk about in type design? There's, of course, comparable. It's a very easy one. Equals equals and not equals. One of the things I really love about work that's going on in the standard library now is that the work to define concepts for the standard library means that we're being much more explicit about enforcing semantics instead of just syntax. Yes, you can write a type where operator equals equals is how you express launch the missiles, but we're not going to pretend that that is a good type or that we support it, right? Just because your code breaks when you did something kooky like that does not mean we care. Is that Marshall laughing in the back? Define these only if you actually mean this type is comparable. And when we are discussing comparable, we also have to have an important tangent into what are you comparing? What is the logical state of your type? For instance, a C++ string can be represented in many different ways, but logically, it doesn't matter how it is represented, it just matters that it is a sequence of characters. The way it was constructed doesn't matter, and the overall allocation doesn't matter. Two strings are equal even if their capacities differ, or one is using small string optimization and the other isn't. The logical state of a string only cares about the logical contents of the value, not the representation, not how you store it. It's what you store, not how you store it. And it is important to separate this notion of representation, the physical state, the data members of T, from the logical state. It is often efficient to represent the logical state with data members that are exactly the physical state, but not always so. The data members of string here could be a pointer and two lengths, 3 pointers, or more complex representations with bit packing to support small string optimization. Regardless of the implementation and choice of data members, all valid implementations of std string have the same logical state. Right? Keep that in mind. Logical state, a little bit of a side note. Types may have this difference between physical and logical state. Design always centers around logical state. Or as Tony Van Eerd would say, you have to know what a type is and what it isn't to implement it. Knowing what it is generally tells you the logical state. The physical state is how you represent and implement that logical state. Once you've decided on a logical state, you can ask the question, should this be comparable? And by default, probably yes. Certainly for types that are primarily about data and not behavior. The standard library already weighs in on the question of which of these is the default. Consider unique pointer. No two unique pointers in a program should have the same non-null value at the same time. And yet, unique pointer is comparable with itself. It doesn't harm anything, nor does it weaken the design of unique pointer to allow it to be comparable like that. It's probably useful in some generic contexts. By the same token, it isn't shocking to encounter types that aren't comparable, but I think it is becoming more unusual. I'd certainly recommend putting some thought into it before deciding not to, especially if you consider your type as having a value as opposed to just being a bucket of behavior. Once you're talking about comparable, you also talk about ordered. Is there a partial or total order for objects of your type? Please don't define an ordering on your type just to put it in a map. Right? If you are defining type chair, it does not get a built-in operator less than just so that you can put it in a map. There is not one true operator less than for chair. I may sort my chairs by comfort, by distance, by number of legs, by color, by seat height, by seat depth. Right? There's many reasonable options for that. If you need to put it in a map, just provide a comparator for your map. Right? That sort order is a property of the storage, not a abstract property of the chair. Of course, there's also the point, ordering depends on the logical state of your type. Right? If you're sorting vectors, you're not sorting them by capacity. And please only define these operators if you're actually defining and ordering. There's 3 reasonable choices here, 3 common choices here. There's totally ordered, reasonable, right? Your type is a big num. Make it comparable, or make it ordered, totally reasonable. There's partially ordered things. You see these a lot in graph theory. Partially ordered is technically the minimum requirement for a lot of things in standard algorithms, but just please don't. Like, please stop writing partially ordered things. Like, it is just such a bug farm. Like, if you're gonna do it with a different name. And it's also perfectly reasonable if you just decide, like, no, this type doesn't have an implicit ordering. Don't make it orderable. All of this will be slightly different, mostly in surface features with operator 20 and operator spaceship. Yay! Yeah, I think that's. There's the question of copyable. Given a T, can you duplicate its logical state into a new T? There's 2 important sort of syntactic constraints here. If you have an operator equals, you had better have a copy constructor. And it is almost always the case that that goes the other way as well. If you have a copy constructor, you should have an operator equals. Not 100%, but like 95, 99%. And it is also important here, the logical state is what is copied. Right? If I ever have a reasonable type and I copy it, and it's also comparable, that assertion had better never fire. Right? That should be an obvious, correct invariant. If you ever screw that up, your type is bad. Okay? Make your types copyable. It's fine. Or make them non-copyable. No judgment. If you aren't sure for some reason, I would say maybe default to making it non-copyable, because it's much easier to allow that later. But most types make them copyable, especially for values. There's this question of mutable. Given a T, can you modify its logical state? And in particular, can you modify its state via operator equals? Most types, yeah, make them mutable. That's perfectly reasonable. And there are a couple rare instances where it is justified to make your type completely immutable. We'll get into that as a holistic design a little bit later. Then there's movable. Maybe. When I started cataloging all of these design properties, movable was important but frustrating. It was, for instance, annoying that the type trait stood is move constructible doesn't really tell you if the type is actually efficiently movable, only whether it can be constructed from a temporary. And that's a case where I had always felt like the type system and the traits machinery were correctly describing syntax, but what I wanted was semantics. But then, with this growing idea that move and copy are an overload set, and that it really doesn't matter, I'm increasingly happy with all of this. Like, just, it is a bug if your copy constructor first invokes Monte Carlo sort. It is similarly a bug if your type could be efficiently moved, but you just chose not to write a move constructor. It's just a performance bug, nothing more. So really, I'm not sure that we should talk about things being movable by having a move constructor. The type trait is actually correct, and as such, I'm implied to lump movable and copyable together, except in cases of move only, but that's later. So we can really go back to the copyable slide and just find replace copyable with copyable or movable, and then we can move on. And then there's invariants, and we start to get less into into syntax and more into semantics, and like what is this type about and how is it implemented? In type design, in many respects, is the question of what invariants are there on the data members of a T and on the usage of a T, right? From a certain perspective, this is the biggest, most important thing. Right? Consider the invariants on vector, right? Vectors invariants include capacity is always greater than or equal to size. Data sub I is a valid T for all I from 0 to size, and isn't for any other data sub I, except for trivial types. Data is a valid and non-null pointer with an allocation of capacity. Right? And some of these are visible in your API, and some of them are internal details. On optional, we get things like if has value, then the member is a constructed and valid T. And if not has value, then the member is not. Right? These are invariants. These are what your type is about. Invariants are why we have data access restrictions, by which I mean public, private, protected. The core guidelines say this straight up. If we want to enforce a relation among members, we need to make them private and enforce that relation, that invariant, through constructors and member functions. The Google C++ style guide takes a much simpler route and just says, for classes, make data members private. That is largely a simplification. There are, for instance, classes where you might have a couple data members that don't participate in any of your type invariants. You could have a silly class like vector plus color, where you could just expose a public color member variable. Like, it doesn't involve itself in any of vector's logic. I guess that's fine. Be a weird class, but like, no reason to necessarily make color private in such a case, because it doesn't interact with anything. That said, that would be weird, right? And a very important thing I've already said a couple times today, don't be weird. Right? For simplicity's sake, we just say, make data members private for classes. Right? It's much easier. No one's going to be like, wait, what? And it's going to be harder to get it wrong. There's a lot to be said for don't be weird. And now we get into novel territory. And a word of warning here, I'm going to use precondition in a slightly squishy fashion, not in standard ease. I'm not differentiating between preconditions, requires clauses, wide and narrow contracts, all of those things. This is already 2 hours of talks. Invariants on a type tend to interact with the preconditions on the interface of that type in ways that we don't usually think of as being part of type design. But just like we saw that const methods blur the lines between micro design and macro design, API preconditions have an impact on the usability of the type in ways that are interesting and not traditionally accounted for. So examples here, what do I mean by precondition and dependent precondition? For instance, the precondition for vector operator square brackets is that the specified index is less than size. Or for optional, accessing the value in an optional requires that it actually has a value. Most types, certainly most good types, are designed in such a way that the preconditions for any API on that type could be checked, could be satisfied with information that is available from the other bits of the API itself. But that said, not all API preconditions are like that. There isn't necessarily a way to ask every question about a value in order to know whether you can use all of the API of that value safely. Sometimes you just have to know by having general knowledge about the rest of the program, like in the case of thread unsafe types. For instance, as an example that we all understand, what are the preconditions for dereferencing an int star? Obviously, the important precondition there is the underlying int must still be valid. And that dereference precondition is different, sort of fundamentally, than the precondition for operator square brackets. One way of describing these differences, again, I'll say this again, all of the precondition on vectors APIs can be verified by interrogating the vector. In this sense, vector is self-contained. Int star, on the other hand, is not. It takes knowledge and invariants that are external to the int star in order to be able to safely operate on a randomly handed to you int star, because some of its APIs have preconditions that are dependent on external factors. And there's some shades of gray here, and there's many examples. But types that have dependent preconditions are, in some sense, harder to use than those that don't. And this comes up particularly often in cases like the aforementioned int star, cases where the dependency is between an instance and some data that is referenced outside of the type, some non-owned external data. Interestingly, in the case of these data sharing preconditions, there's also still a connection back to the thread safety of the type. You cannot really talk about thread safety of these types without potentially including what they are depending upon. You cannot read through a dereferenced int star without synchronization or structural knowledge that proves not only that the int star is okay, but that the underlying int is okay. Otherwise, you get data races. Going back to our categories of thread safe, int star isn't even really thread unsafe because there are APIs on it that cannot necessarily be called safely, even if the access to the int star is protected by a mutex. Because it has preconditions that depend on data outside of the type, thread safety of int star is more than the API of just int star. We have to consider everything that it is dependent upon. It's a lot of words for a hopefully clear concept. And again, compare that to vector. For vector, we know that we are safe from races by knowing only that the vector has not been shared. It takes manifestly less knowledge to operate on a vector safely than on an int star. This is part of why we just like vectors better than, old C-style arrays. We have to remember, everything is thread compatible, not thread safe. This is not a language that is going to baby you. And valid programs don't have data races. The most important structural piece, the one that we rely on all the time when we are discussing types, is whether we know, or that we know that an object is potentially shared or aliased. It is so ubiquitous that we assume that given a single object, it's not shared when we're describing its design, that is just straight up the default. Right? The default when we're talking about type design is, well, this isn't being written to by someone else. Otherwise, all bets are off. But for every single type, we have to have some form of knowledge about why it is safe to operate on an instance of it by reference. That could be the easy form of knowledge, it's not shared, or it could be a harder form of knowledge. It is not shared, and everything it is dependent upon is also not shared. Whether we have a dependent precondition is a property that we're only really sort of beginning to talk about. I don't love the terminology. I hate naming these things. But the majority of the types in the standard avoid this issue, containers, optional, variant, but not all of them. Right? C++17 introduced string view, which definitely has preconditions like this. And so does span, which is in the current C++20 draft. But I've been getting a lot of mileage out of this idea of prefer types without dependent preconditions this year. And this idea is showing up in last-minute changes to std span, among other things. So I think that it is safe to say we can and should definitely favor types that have no such preconditions. Introduce those without concern. Introduce dependent preconditions only after some significant thought and design work. They aren't so bad as to be avoided at all cost, but you should understand what those costs are going to be. And it's important to note that this is more than just, do I have an unowned, maybe shared pointer member? Any API on your type that has preconditions that aren't checkable by other interfaces on your type causes some additional difficulty to use it. So it's a good idea when you have a draft of your API and all of the preconditions of your APIs to go through and sanity check that. Have you provided enough accessors for a user to be able to use this type easily? I know for a fact that Library Evolution approved types over the summer that have dependent preconditions, things like atomic barriers or latches that are counting down, providing a user the access to see what the current value of that counter is would actually be out of the spirit of the type, because by the time you query it, the answer is probably wrong. Right? And so we consciously chose it's okay for you to have preconditions that you can't query by just access to the type. The difficulty of that domain justifies the slightly harder to use API. So that gives us sort of a taxonomy of properties that we can discuss when we're talking about types that are well designed. I'd argue that if you describe a type, or at least a value type, by telling me how it behaves in all of these dimensions, I can probably get a pretty good understanding of that type. And when we start doing that operation, we start seeing patterns. That is, configurations in this configuration space that go nicely together, that come up over and over again. For instance, of course, there is regular. Regular is usually defined by looking at the set of properties that are required in order to use types safely in standard algorithms or ranges. Or alternatively, regular is what we mean when we say do what int does. For this talk, I'm going to use the definition of regular that is actually in the working draft that came into the standard with standard library concepts, because it's actually part of the standard. It is similar to the older literature on Alex Stepnov's definition of regular, but slightly more limited. It doesn't require ordering, doesn't require less than. I'm also mostly going to ignore swappable. It's primarily a syntactic thing more than like a deep feature of your type. If your type is mutable and either movable or copyable, make it swappable. I have not ever come up with a reason not to do so. But these are specifically the concept requirements of a type to be regular as per the current draft standard. So let's look at regular. Based on those syntactic properties, we get example snippets that show how regular types behave regularly. And if we look at that snippet with specific types, we can see int is regular. It is worth looking at this for a second, right? It might take you a little work. But if you stare at this long enough, I think you can find that for a snippet like this, there is no implementation of some t or do stuff that can make an assertion fire without getting into UB somewhere, right? You can't const cast away that const reference because the object was declared const. Now you're in UB if you like try to mutate it after the fact, right? Everyone see that this is definitely fine for int? Mostly I'm stalling so I can take a drink of water. And int star is regular-ish. If we stick to comparison and all of those operations, it's totally fine. But if we dereference the pointer, which is actually what pointers are usually there for, then this snippet might have a data race and be UB. And once it's UB, I could probably get the assertion to fire. There are threads in the program, then we don't know if that underlying int is being mutated. It requires external knowledge, knowledge more than just knowledge contained in the type, to state that this snippet is correct. And even in a single-threaded program, it's actually implementation defined whether you can equality compare a pointer after deleting it. If do stuff is actually just calling delete on it, then this snippet is no longer actually portable and the assertion may still fire. At the same time, though, int star is copyable, movable, default constructible, assignable, comparable. It meets the normal stated requirements of regular, but our snippet is borked, and that is unhappy. Right? There's something important about dependent preconditions, about the structure of the program, and about preconditions on the API that are required by regular, like the comparison operator in this example. Ooh, skipped. Interestingly, this also ties back to thread safety and const. If we use a really, truly horrible type, like from the previous talk, where all of the methods are const qualified and all of the members are mutable, then this call to do stuff can actually be mutating it. And further, could be kicking off threads, which would make this not only an assertion failure, but a data race and UB. Right? You can get arbitrarily bad when const doesn't mean const. And this shows us that even types that obey the syntactic requirements of regular generally still require some deeper knowledge that is external to the type. Could either be something squishy like const means const, or something formal like thread compatibility. And in the case where there are data dependencies outside of the type, like for pointers, that thread compatibility is ill-defined or at least problematic. And the same is true of string view. If we're operating on a string view without data races or use after free, that is, if we're operating on a string view in a program that's not a bug, then we know that operator equals equals doesn't race, and we know that the underlying buffer still exists and isn't being mutated. Conveniently, that is what we know for the common use case of string view. You're passing it as a parameter to a function. So long as you don't kick off a new thread, you should be pretty sure that the underlying buffer still lives and isn't being mutated. You're certainly in no more danger than you would be with const string ref. So long as we have that external knowledge that the buffer still exists and isn't being mutated, string view is still regular. It's copyable, movable, swappable, default constructible, assignable, comparable. The APIs on string view that have no dependent preconditions are thread compatible, like remove prefix and remove suffix. You can trim a string view. The APIs that do have dependent preconditions, like operator equals equals or operator square brackets, are thread compatible only when taken with the underlying buffer, with additional external knowledge. Does that mean that string view is regular? Of course not in the same way. This is highly predicated on, do we have that external knowledge? Do we have that structural knowledge? And the form of that knowledge, the scale of that knowledge, is much harder than when you just have a string or a vector. Where does that leave us? Re-examine the requirements. These are the stated requirements for regular. These describe the requirements for a type that you could put in a really crappy set, a set that doesn't store its members in ordered fashion, but whose members are unique via comparable. Then there is an implicit requirement. It is the implicit requirement on all types always, that you are using it without races. All of the explicit requirements are applying some semantic requirement to the syntax that we expect for values. The implied requirement feels different. It is about how the type interacts with the rest of the program. And now we tie this back to our weird prelude. One of these things is not like the others. One of these things is explicitly about global structure, is the plain flat. And to me, there's an obvious parallel when we talk about the implicit requirement on regular types. We have some options when we define how we know that it is safe to use an instance of that type. We can have race-free use in several ways. The best types are thread compatible or thread safe and have no dependent preconditions. All we need to know is that T itself is being used race-free. If you think back to the snippet, we saw it constructed as const and passed as const, or by making or by value making a copy. In any case, if it is thread compatible and self-contained, we know that this snippet will always be fine. Some types with dependent preconditions, may require that we know that T and its dependencies are used in a race-free fashion. Second bullet. If we know that, we can still reason about the type, but it is, of course, harder to know that. Or sometimes we could know that the program is single-threaded, or that the type can only be used single-threadedly, like it lives in thread local storage or something. And I really like this approach for enumerating the variations on the implied requirement for regular. I'm not saying that regular types, as we have understood them for years, are wrong. Euclidean geometry is the correct default. But there are other geometries that are self-consistent and worth discussing. And importantly, when we recognize that our parallel to the parallel postulate has some options, we can start investigating the resulting design space. Value types, types with no dependent preconditions, types that we think are good, should default to regular. Or maybe we'll call it Stepanov or Euclidean regular. Right? Those are going to be the easiest and best, and they work well. They require the least knowledge. If your type is going to have dependent preconditions, those are best when they aren't preconditions on any of the APIs that intersect with regular. Right? Regular requires operator equals equals and assignment and things like that. If those operations have dependent preconditions, your type is going to be bonus hard. Right? Think very carefully before going down that route. In that sense, int star is mostly better than string view because operator equals equals is mostly free of dependent preconditions. Hand waving around that implementation defined behavior for deleting a pointer. But because its comparison operator has dependent preconditions, string view is not Stepanov regular, but it is still useful. We just need mechanisms to describe the difference between it as a useful but sharp-edged type and types that are truly irregular and actually garbage. String view is not Stepanov regular, but maybe it is non-Euclidean regular. For comparison, span, as it is usually formulated, is not even as regular as string view. One of the major differences between string view and formulations of span is that you can mutate through a span, even a const span, and you can never mutate through a string view. And this turns out to be enough to make things fall apart. Consider this snippet. For most formulations of span, it is perfectly fine for me to increment that element in the span. and then my assertion is going to fail. We could try to fix this. We can try to modify span so that a const span only gives you const access, but we still have a problem. Span is shallow copy, so it is cheap and easy to make a copy of it and then mutate through the non-const copy. I've said a few times today, one of the things we rely on when we discuss types and design is that const means const. And for reference-like types, we run up against a hard truth of C++ type design, that you can only have 2 of these 3 properties. You cannot have all 3. And when you have types like span that try to lump them all together, it's sort of broken by design. And the practical side effect of this is not actually theoretical. Over time, we see more issues and more usability bugs per line of code that uses span than in using string view, and more when using string view than when using string. But this is specifically because span is not as regular as string view. Span is not regular. No matter what structural knowledge you have of your program and about the underlying data, you cannot make span regular. This, interestingly, I think, also touches a little bit on the smart references debate, where my answer is just say no to smart references until those types are actually the same. They're not, and smart references is doomed to be annoying until we get that right. Anyway, enough of that. Going back to regular and harping on this just one more time. The best types are regular as we've always known it. A second class of those, to my mind, are regular when combined with some additional structural knowledge, things like string view. Avoid types that aren't regular regardless of what structural knowledge you have. Span needs work. It syntactically tries to be regular and then fails. Let's look at other families of types that actually work nicely. It's been suggested to me from Matt Calabrese that anything that is a subset of regular is probably okay. And once he said that, it turns out that all of my examples, I think, are actually just a subset of regular. So, for instance, there's semi-regular in terms of standard library concepts. This is all of regular except comparable. These are the objects that can be treated as values minus comparability. It's roughly the set of types that you can put in a vector. This is commonly raised as a more traditional correct design for a type like span. If it can't deep compare, just don't make it comparable. That would help. Once in a while, you'll want to put together a type that is immutable from construction. These are really handy in those rare cases because they are thread safe without synchronization. If it can never be mutated, you can always pass it around, and you know that everyone is going to have at most reads into it. Of course, you pay for that with the fact that you can't move from or swap them. If you pass them around very much, you're paying performance in copy overhead instead of synchronization overhead. This is the exception to the rule of if you have a copy constructor, you should have an assignment operator, unless you are specifically doing this. The other way around is always true. There's the most C++11 of all new types, the move-only type. These almost always represent some finite resource, memory, hardware, network, whatever. There is definitely going to be some interesting data invariant or API preconditions on this type. This is going to have some intersection with the structure of your program, right? Considering the amount that we discuss move-only types, it's basically unique pointer or logically equivalent bundles of resources, and very little else. If you aren't asserting unique ownership of something, new types should rarely be move-only, and should probably have like a real API review before you go down this path. There's, I won't say good, but common types, your business logic types, the ones that are, most code bases are just chock full of. These are more like objects than values. It's kind of a bundle of behavior as opposed to a bundle of data. These can often be justified to be either thread safe or thread compatible, depending on your scenario. They really probably shouldn't be comparable or assignable. They should be grouping all of the behavior of your program or your subsystem and just operating on incoming values, hopefully values that follow some of the aforementioned designs. Or there's structs. Struct is really, in this model, a type that has no invariants that must be upheld. None of its data members will ever be part of an invariant without extensive refactoring. This tends to inherit the default behaviors for copy and comparison from the language based on their component members. The essence of struct in design is fundamentally it has no invariance. And the standard gives us a clear example of this in pair. Right? Pair does not have accessors, it just has .first and .second, because the standard, because pair, doesn't try to assert any invariance over pair. Right? You may, at one point when you were younger, have tried to use pair as a lightweight, I didn't feel like defining a thing, and started having invariance on first and second. And that went poorly for you. Right? You wanted them to be sorted, and then you passed it to something, and some fool mutated it, and it stopped being sorted, right? And badness happened, right? And the reason badness happened is because you had a type that was designed to express no invariance, and then you asked for there to be invariance, right? That is what struct is. Also, given that I think an awful lot about code bases in long time spans, will ever is an important clause on this slide. It's been like 2 weeks since the last time I heard a story of, well, we were just doing this with structs because it was easy, and now we need to refactor a thing, and there's no setters and getters, there's no choke points. And so we cannot change it because we cannot add invariance after the fact, and we're in pain. Be careful with structs. And then there's this big question that I have devoted so many words to, right? Are reference types okay? If so, I think they really need to look like string view and not span. I think we've got good experience and now theory to explain why string view is acceptable, not as good as Stepanov regular, not as good as vector, not as good as string, but acceptable, and why traditional formulations of span are just borked. String view is copyable, movable, swappable, default, constructible, assignable, comparable with dependent preconditions. That's the trick. And that leaves us with a bunch of open questions, right? What is the future for reference parameters? Reference parameters are the thing that most heavily, most subtly ties both halves of this talk together. Because we are going to, I almost guarantee, build more and more reference parameter vocabulary types, like string view, like any span, like set view, like stood function, like function ref. And we need to understand how to design those properly, or as best as we can, because the rules that we have followed for so many years of always be Stepanov regular make us pay for copies that we do not want. Are we okay with string view? As a community, we're going to have to discuss that a bit. How do we design something like span? How do we design string view's friend that operates on T generally and maybe mutably? And importantly, how does this notion of types with dependent preconditions affect how we think about design theory? I will plug the essay form of this talk. See revisiting regular types on abseil.io. I think if you just Google for revisiting regular types, you'll find that. This hopefully explains it in slightly different terms and with slightly different examples. If you didn't quite follow along for some of the more theoretical bits, maybe check through there. And lots of time for questions. Thank you. There are microphones in front of both aisles. The question was, is double regular? And this is, double is, I think, actually regular with preconditions. And that precondition is there are no inf or nan. And if you can avoid the creation of a nan, then double is absolutely lovely and regular, right? But I think the dependent precondition, machinery and out, actually helps resolve this annoyance of double and regular, for once, because it has always been the case, double isn't actually regular, except it always is, right? And now we have a way to actually express that, I think. So it's one of the reasons why I like this. So, guys over here, yeah.
Hi, sorry. So one of your points was, don't define comparison operators just because you want to put things in a map or whatnot. So I actually agree with that, but I feel like the standard sort of does this to take two examples, unique pointer and optional. They're both kind of types where, I've never seen valid code that just randomly decides to compare, like inequality compare to unique pointers, like A less than B. With optional, it's kind of similar. Like you have this really arbitrary decision about is an empty optional smaller than any value or bigger than any value? So I feel in both these cases there's very little valid code that would depend on directly comparing these. But one of the big arguments is you want to put these things in maps, you want to be able to sort them and binary search them, and here we are. So do you think that this is valid, or do you think they just have comparison for containers and?
I think that's a great question, and I think the answer is a little bit of both, specifically in that I think you should define your ordering if there is one true obvious ordering. And for unique pointer, there is, modulo all of the committee hoopla about pointer comparison things, but that's fairly esoteric. For optional, as long as you just pick one, I don't think anyone super cares if it's smaller or bigger than all of the t's. So I don't think it's actually fundamentally wrong for either of those to be comparable, but I would also argue that the reason so that you could put it in a map is always a terrible reason, right? I would flat out say, that is not the reason that those are okay. Because I completely agree, that's not a good reason to do comparison on anything. I think it's just, there's not a good reason against, this is the clear way that these things compare. I think there's almost certainly other examples of things in the standard where we may have taken shortcuts to make it easier to put things in a map from back when it was harder to declare how to have a comparator for a map. So in many cases, the standard is not perfect.
Thank you.
Yeah. Nobody over there. So.
Hi. First of all, thank you for the talk. There was very, very interesting food for thought there. I actually have a question to something that you said in the very beginning of the first part, where you said if you're passing an rvalue parameter to a function, what that communicates to the outside is that you may move.
Yep.
And while I think that is technically correct, I would probably get pretty upset if, bar some catastrophic failure that prevents the function from doing its job properly, if it would not actually move from an rvalue parameter. Do you agree with that, or is there just some scenario that I did not think about where it would be valid to accept an rvalue parameter but then not move from it?
So the standard has prior art on this. There are types, or there are interfaces that are specifically try something. So for example, I think it's the RCU paper that's progressing right now, has a try update where it takes a unique pointer ref, and if it is possible to do the update, it is moved from. And if it is not possible, it returns false, and you are left with, you maintain ownership. There is no other way to express that. Okay, right? There are other ways to pass a thing, right? And if you are passing a thing as a value or as an overload set with ref, right? I have no problem with that, right? Because the overload set makes you say, well, the semantics are not maybe move because you have a const ref of it, right? It's just in the individual case of ref by itself, that is reserved for maybe move.
Okay, but then this try case, that I would consider that this catastrophic failure thing where the function is by some external circumstance prevented from doing its job, and that's why you don't want to mess up the caller even more by moving the thing away and then not doing your job.
Maybe.
But besides from that, you would agree that if it takes it by rvalue reference, it probably it should at least do a best effort to actually move.
Yes, I would just say there's a difference there between arguing about the design of it versus arguing about the implementation of it.
Yeah.
And at the design level, ref by itself, not in an overload set, is maybe move, period, full stop. Right? You had better be trying to move, and it had better not be well, every once in a while I'll move. That's just going to be daft, but
Okay.
yeah.
Thank you.
Yep. Still no one over here. Yep, go for it.
You talked mostly about members with data, and then you mentioned offhand all kinds of types which are logic, right? But from all the systems I've seen, 90% of the ideas of the system, the actual sophisticated logic inside those kind of classes, which are not comparable, not sortable, not necessarily default constructible, a lot of singletons, a lot of those kind of classes. The question, is that a bad design?
No.
Should have been a separation. This is a class and this is different semantics here.
I am very much a descriptivist, right? I see all of the things that we use, that we work with, that don't fall apart, that don't shoot us in the foot. And I say, well, if those are all working pretty well, there must be a reason why that is okay, right? So there might be a prescriptivist in design that says, no, all of your things must be values, and you haven't found the right design. But practically speaking, I think for for almost all use cases I've ever seen, there is some chunk, some glob of business logic in your program, right? And lumping that together somewhere is reasonable, right? I may have beef with your, using singletons, that's going to come back to haunt you, but beyond that, there's not a type design problem necessarily, right? So there's business logic types. Don't treat them as values. Understand that different rules apply, and get your business logic right. Write good tests. I got nothing more.
Okay.
Yeah.
So when you were talking about span being permanently broken, you had a slide about pick 2 out of 3, and that went by really quick. I was just wondering if you could show it again.
And I have a longer, slightly more explained version of this in the essay that I cited there. And once I posted that, I probably got half a dozen or more people tried to send me a tweak of span that is rigged so that when you have a const span, you can only copy it as span of const t. And the problem there is even basic things like auto copy equals other span fails. Because things just don't actually deduce properly, and the language machinery does not allow us to do this properly at this point. So, Eric.
There was a mighty battle in the committee over span and this particular design, and I could have sworn that we killed the comparison operators on span. I'm misremembering this, or?
I don't recall entirely. I think they're in there, but Tony has a paper in Rapperswil where we basically granted him just come back to us and fix it, because there are many different appropriate fixes, and I think we took preference votes on which of those fixes to do, and any of them would be better than leaving it where it was. Yes. So it is possible that they get pulled out. It's possible that they become shallow compare. It's not deep compare. It is possible that we rename it spanning putter, because in some sense it is more of a pointer range. Yeah, span will not ship the way that it is, and it is probably the case that GSL is going to have to catch up.
Good, because I couldn't believe it, and I just looked it up on CppReference, and you're right, all the deep comparison operators are there, and I was shocked and horrified.
Yeah. So, yeah, span will
kill it with fire.
Span will get killed with fire before we ship it.
Good.
Yeah. So.
Hi. Regarding regular types, one of the properties of a regular type is default constructability. I'm wondering why that's important. If it's just to copy what int does, I mean, int isn't usefully default constructible, and lots of types are all those other things, but not default constructible.
There has been sort of a growing desire to maybe revisit that question in particular. Arthur talks about that kind of a lot. And fundamentally, I'm a little tempted, but I have not found, I've not thought about it deeply enough to go, to weigh in either direction. And I sort of think it so rarely affects the design of your type to have it be default constructible that
one thing about
it's very little cost.
You mentioned that being able to be used in a vector, for example.
Yeah.
And in C++11, I think the only time that your t in a vector needed to be default constructible is if you were using resize, because the default argument, the second argument, had to be default constructible by default.
Right.
And that was changed to be 2 overloads, so that there was no default argument anymore. So, yeah. I'm just wondering how important that is these days.
I think it is. I mean, the fact that I can't come up with a argument for specifically why it is important suggests that it's maybe not the most important, but it's also not hurting much. So I suspect it's probably too late in the game to pull it. There's also the argument that 9 times out of 10, your moved from state is going to be your default constructed state. So if you're going to pull default constructed out of the requirements, the set of people that can actually use that are going to be types that aren't movable.
Well, it can still be copyable, though. So.
I mean, it still could be, yeah, but you're not buying much by making that simplification, I think. So I don't know. There's some thoughts to be had there, but I don't know.
Okay, thanks.
Yep. Other questions? Perfect. Right on time. Thank you all very much.